Hey everybody, welcome back. It's Lieutenant Kearney again. In the last video, we talked all about the different types of magnetism at play on our vessels to include our permanent magnetism, subpermanent magnetism, and induced magnetism. We also chatted about how to minimize those to the maximum extent so that the overall ship's signature is as minimal as possible. During this video, we're going to talk about how all of that comes together in what we call the ship's deviation. Now, when we combine induced magnetism, subpermanent magnetism, and permanent magnetism, we get our overall ship's magnetic signature, and the impact that it has on our compass is what we call deviation. So it's going to be that deflection left or right of our magnetic meridian, and that's going to be caused by the magnetic properties of our vessel. Now, thinking back, we learned that the variation is caused by a deflection left or right of our magnetic meridian caused by the magnetic forces of the Earth. Our deviation can either complement that, so bring our compass needle further from the magnetic meridian, or it can counteract the force of the Earth's magnetism and bring our compass closer to the magnetic pole. Now, every ship should have deviation tables, which is going to list your deviation on all the different headings around the compass. Now, this is going to be an inspectable item for both you and the electricians. So knowing where this is located, whether or not that's down in CCS or up on the bridge, maybe in a safe, is going to be really important for both you and the engineers. Here we have an example of a deviation table from one of the Coast Guard cutters. So if we look at the bottom of our screen, it looks like we have, when we're on course 000, we have a deviation of 1 degree west. So our compass is deflected 1 degree to the west of our magnetic meridian based on the deviation of our vessel. As we can see, based on which heading our ship was steadied up on, we see a different deviation listed. With a traditional magnetic compass, updating these deviation tables was very, very time consuming. So essentially what would happen is you would have to swing the ship, which is setting up on each one of these courses individually. We would then have to calculate the deviation while steady on that course at a constant speed. And then we would have to make adjustments to our compass to decrease the amount of impact that our deviation had. Whenever we would make an adjustment to our magnetic compass, we would then have to swing the ship again to recalculate the deviation. And then we would have to do this for every one of the compasses that we had on board. Now, when you get to your ship, there is a PMS check that's associated with the compasses on your ribs, in which you will have to swing the ship to determine the deviation for that specific compass. Other navies, as well as our ribs, do still use the traditional magnetic compass as their primary compass on that vessel, in which case they will have to do just this to update their deviation tables in accordance with the governing procedures. Now, most of you at SurfNav will be going to a vessel that does not use a traditional compass as their primary compass. Many of you will use what's called a DFGMC or digital flux gate magnetic compass. Now, over the last 2 videos, you might be thinking traditional magnetic compasses is painstakingly time consuming. Not only do we need to determine the variation for the area that we're operating in, but then we would also have to determine the deviation that we would experience on different courses. We'd have to continuously update our degaussing, which just complicates the process even more. And so new technology has advanced to make this process slightly easier. With the advancement of technology, a lot of these processes have been streamlined for us. The DFGMC is going to be the most common magnetic compass that we're going to see on US Navy vessels. There are a couple different iterations out there. So when you get to your ship, make sure you are familiar with your specific configuration and your specific system. However, these do give us a lot of benefits. Number one is those compass cards that we talked about a few slides ago are going to be automatically updated by the algorithms and then stored in the DFGMC. So although we are still required to keep our magnetic compass cards on board, they will be updated in a much faster and streamlined process. Furthermore, we can have a remote readout separate from the sensor itself. So many ships will have their DFGMC sensor located on the mast or a yardarm. And this is going to be beneficial because it's going to be the furthest point from the magnetic field of our ship. That's going to decrease the impact that deviation has on the sensor itself, while still giving us the benefit of being able to read the magnetic heading from a central location like the bridge. Lastly, because the algorithms have stored the deviation within the system itself, our DFGMC will automatically account for that deviation. So instead of having to account for both variation and deviation while trying to calculate our magnetic heading, we won't need to account for our deviation because the system will automatically incorporate it when reading out our magnetic heading. So we will still need to account for the variation in that specific area, but it's a little less math that we need to do as NAVs and ANAVs and as bridge watchstanders. Every ship is slightly different. You might have a slightly different configuration or a slightly different iteration of the DFGMC, but generally you will have a remote readout as well as a remote control for your system. Now, that being said, even though we do have a lot of benefits by increasing the technology with the DFGMC, we do still have to update it to ensure that those algorithms are accurate. When you get to your ship, make sure you're doing these updates in accordance with the PMS for your system. However, generally this is going to be done 48 hours after getting underway or 24 hours before any special evolution that you might be planning on doing. Generally, this is going to involve changing the calibration setting. During our normal underway steaming, typically this is going to be set to auto so that we are constantly updating those algorithms. However, when we are intentionally calibrating our compass, we're going to set this to on. We will then doing several slow circles at a constant rate. Typically, you're going to get an indication of when your PMS check is complete with a few short beeps from the remote control itself, indicating that a new calibration has been set. You will also typically get a calibration score. So this first digit is going to indicate the quality of the compensation, 9 being the best. The next digit is going to give you the quality of your DFGMC sensor location. In this case, it's a 6, so it's a okay location. This will normally not change. The last digit is just going to be a running ticker of how many calibrations you have done. If we had a new calibration, this would increase to the digit of 2. Now that we have a good understanding of the different types of magnetism at play on our magnetic compass, in the next video, we'll learn how to look at this holistically and account for it on the bridge.